Real-world scalable entity resolution. Hi, I'm Nick Bates-House, Chief Architect at Tamer. Welcome to part 4 of our 5-part series on entity resolution at scale. In part 1, we talked about why entity resolution at scale is hard, covering some of the challenges that need to be addressed, and looking at some measures of success, including being able to deduplicate 500 million records representing the entire United States population in under 3 hours for under $300 on commodity scale-out infrastructure. We also observed that we can process a 1% delta against those 500 million records quickly and with stable IDs. In part 2, making the easy part cheap, we looked at pre-grouping, feature extraction, and blocking that deal with obvious matches and obvious non-matches quickly and cheaply, reducing the amount of work that machine learning needs to address from those 500 million input records down to fewer than 1 million pairs. In part 3, the hard part, we looked at how we do handle those 1 million pairs, looking at signals, similarity clusters, and record consolidation. For metrics of success, we reiterated the ability to deduplicate the US population for under $300, but also observed that that $300 value is consistent across many different scales of scale-out infrastructure. In this part, we're going to talk about effective learning. We'll start with some definitions. What do we mean by effective and what do we mean by learning? We'll go through the machine learning workflow and then again talk about some metrics for success. So what do we mean by effective and what do we mean by learning? Effective means learning from rare events. Keep in mind on these very large-scale data sets, the true matches are extremely rare. The information space is dominated by non-matches, by obvious non-matches. In Febrile, the Febrile data set that we're using for the 500 million test data set for the entire population of the United States, approximately 1 in 1,000 records is interesting. Interesting here means that there is some other record in the data set that is similar without being an obvious match or an obvious non-match. The traditional train test cycle may take hours to days, so to accumulate the 5,000 to 10,000 training labels at that 1 in 1,000 interesting record rate may take weeks to months and potentially years. So to learn effectively, we need to find these interesting records quickly at scale. For learning, the hallmark of learning is accuracy and increasing accuracy with additional training. One of the challenges here is that accuracy is really hard to determine without ground truth. We do not have extensive ground truth for these real-world data sets. An extensive manual review is cost prohibitive. Our subject matter experts' time is extremely valuable. So we need some approximate measures, but many approximate metrics fail at large scale. For example, we observed in part 1 that a classifier that says non-match will be 99.99% accurate for record-oriented approximate metrics. If instead we measure whether records are clustered together correctly, large clusters will dominate the results. Getting a single large cluster correct has k-squared correct pairs, and other smaller clusters will be kind of lost in that accuracy measurement. So it's really hard to measure accuracy at scale, but learning really is about increasing accuracy over time and maintaining that accuracy stable over change. So what is our machine learning workflow? The machine learning workflow has 3 phases. We start with the bootstrap phase, where we start with little to no information, and we're working very closely with a subject matter expert, an SME, to create some initial models. Once we have those initial models, we can enter a refinement phase, where we're going through this iterative cycle of gathering additional information about inaccuracies in the previous version of the model and adding to the training data to create a new model that has greater accuracy. And then once refinement has converged on a high accuracy model, we then produce validation metrics that help the rest of the organization understand the extent to which they can trust the output of this workflow. So we'll go through each of these steps in a little bit of detail. The first step in the bootstrap is to address data scale. Whatever we do, processing 500 million records is going to take a lot of time. So we want to reduce the data scale in order to minimize the cycle time during these early iterations. One of the challenges here is that random sampling makes rare events even rarer. Random sampling makes our hard problem even harder. On the other hand, model-guided sampling, using information from the model to try to filter down to a subset of the data that is likely to have matches, tends to reinforce whatever bias is in that model. So we don't really want to use either of those approaches, but we need to reduce the data scale somehow. The approach that we've taken is to work with the subject matter expert to find a data subset based on some other criterion in the data. So the subject matter expert selects a somewhat representative subset. This is only somewhat representative. It doesn't need to be perfect. We will address bias in the data as the scale increases. And a common example here is to filter to a single geography, maybe start with a single city. Once we've filtered the data down to a sufficiently small scale that we can iterate quickly for the first couple of generations, we need to create the unsupervised models. These are the models that we covered in part 2, making the easy part cheap. One of the challenges here is that if we start with poor recall, it can be really hard to recover that recall in later cycles of the refinement. So the approach that we use during this phase is to use an SME-guided blocking model. We work closely with that subject matter expert to come up with high recall clauses in a blocking model, and to leave the other unsupervised learning more or less at default. Pre-grouping, we can omit on small-scale data, fewer than 1 million records. Pre-grouping will have an effect, but we'll be able to run efficiently without pre-grouping. That's okay. Record consolidation, we can leave as a default model, just using most common value until our clusters converge, and it starts to get interesting to tune the clauses in our consolidation model. So we work with the subject matter expert to create a very high recall blocking model. We might use some estimation in the data in order to tune those blocking clauses, making sure they're not producing something close to an n-squared pairs result. But we're not too worried about that because the reduced data scale that we're working with will mitigate any performance issues. Once we have those unsupervised models, we need to build enough training data to train a supervised model. One of the challenges here is that most pairs at this early stage will be obvious. So even though our blocking model has already eliminated most non-obvious matches, we don't have a pre-grouping model. So when we're looking at the pairs produced by blocking, most of the matches are going to be obvious. Subject matter experts are also rarely trained for this kind of data analysis. They're going to need some help navigating through these early results to try to find these very rare, interesting match cases. So our approach is to work closely with the subject matter expert to gather just enough training data. We have a user interface that facilitates search and filter to find these rare events. And in particular, we want to be able to find, for example, pairs of records where name is similar but not identical between the two records, and address is similar but not identical between these two records. And we work with the subject matter expert to find these rare, interesting cases so that we can find 25 true matches that are not identical and 25 true non-matches that are similar. This is not enough training data to build a good model, but with oversampling, we have enough training data to build a model that is good enough to get started. Now that we have unsupervised and supervised models, we're ready to enter the refinement phase of the machine learning workflow. The first step in the refinement phase is to apply the models that we have against the full data. We've accumulated training data. We need to actually generate the signals, the pairwise similarity, and the clusters for the full-scale data that we have. Again, this is the subset of data that we filtered down to. We have many models. There's a lot of high algorithmic complexity with potentially large intermediate data sets here. And our approach, which is divide and conquer to break this into subproblems, is covered in parts 2 and 3 of this whole series. So I'm not going to cover those in detail here. Once we've applied the model, we can gather subject matter expert verification and correction on the results. So the two traditional challenges in this kind of machine learning training exercise is we tend to have over clustering or under clustering or a combination of both, right? Over clustering, we might have a pre-grouping model, pre-group by, or a classifier that are too aggressive. They're putting records into clusters that don't belong together. Under clustering is typically from blocking that is too restrictive, or the classifier is missing cases and is putting records in separate clusters when they should be clustered together. We provide subject matter experts with a user interface that allows them to directly, again, filter according to values, signals, and similarity to find scenarios that they are familiar with. They have a lot of contextual knowledge. They can go and find the training data that they put in, see how that turned out, but go and find cases based on their own knowledge and their understanding of the domain where they can correct the output of the machine learning. That results in cluster verification. The subject matter expert verifies that records are correctly clustered together, or it moves those records when they're incorrectly clustered, move them into the correct cluster to fix the clustering and verify that they belong in the cluster that they've been moved to. And then, as mentioned, the subject matter expert wants to also go in and review the training labels. As they come to understand the problem and the data better, they may want to tweak those training labels. So that's subject matter expert review of the direct results of the model. The next thing that we want is for the system to request input from the subject matter expert to facilitate active learning. This is the system trying to gather information that is going to help it resolve uncertain cases where its confidence is low. So we want to find training labels. We want to find pairs that can serve as training labels where it's most needed. We need to find these rare events and present them to the subject matter expert. One of the challenges here is that subject matter experts are most comfortable correcting clusters rather than pairs. So we want to present clusters to the subject matter experts and say, hey, all of these records represent the same entity? And if not, move the wrong ones out of the cluster into the proper entity. The way we do this, our approach, is to label a sample of low confidence clusters and pairs without bias towards large clusters and without bias towards common pairs. And then we compute cluster confidence as the harmonic mean of intra and intercluster confidence. So cluster confidence we introduced in part 3 of the talk, which is 1 minus the entropy of the probability of match. And we can combine intra-cluster confidence and intercluster confidence into a single aggregate cluster confidence metric using the harmonic mean. Naively, intra-cluster confidence and intercluster confidence are order of E squared. That's the number of edges in the cluster, or the number of edges between a cluster and other clusters, which can be huge. There are nice approximations that are E log E, where we're looking at just the edges that have been produced by pair generation and just the edges that are anchored in that cluster. So an efficient approximation of cluster confidence, and then we're able to use that confidence to highlight or to identify those cases where the model isn't able to produce a confident result, a confident classification of match or non-match, and present those to the subject matter expert for labeling. For pair confidence, we can just use the entropy of the submodel disagreement on that particular pair, and we can prioritize active learning labels to present to the subject matter expert based on that pair confidence. The next step in refinement is to increase the data scale. In the bootstrap phase, we restricted to a relatively small subset of the data. We want to increase the amount of data. Some of the challenges that we run into as we do this is that blocking may be too loose. We optimize blocking for high recall, not for pruning, so we can end up with excessive blocks per record, or our pre-group by can be too strict and we can end up with excessive records per block. Either of those can end up producing too many pairs. So the way that we approach this is we incrementally increase the scale of data. If we started with a single geography, we might add a second geography, for example. We're not doing all geographies, we're just adding a second one. And then again, we use estimates to guide the tuning of models in response to that additional data. Once we have increased the data scale, we can come back and address pre-grouping. One of the challenges in changing pre-grouping is that changing our pre-grouping criteria can eliminate pairs. A subject matter expert during review of the machine learning output might change their notion of what constitutes an obvious match. Now we need to go back into pre-grouping and tune the blocking key, the grouping columns. But pair labels are on pairs of representative records, and if we have different grouping keys, then we have different representative records. Doing this naively, we could lose all of the training data that we've accumulated so far and need to start over. That's awful. Working with our subject matter experts is one of the most expensive things that we do. We really need to treasure the human input that we're getting from subject matter experts. So we want to do everything that we can to preserve these high effort labels that they've put into the system. So our approach is to migrate those labels from the old representative records to the new representative records. We do this by exploding representative records back into their source records. We take the cross of the source records for each of the representative records in a pair, label each of those pairs of source records now with the same label that the pair of representative records had. And now we can collect those source records back onto the new representative records according to how they've been grouped. And that will accumulate the labels for those records onto the pairs of new representative records. In those cases where we have unanimous labels, we keep that as a training label. In cases where we do not have unanimous labels, a mix of match and non-match labels, we just discard that label. And we just discard that label rather than trying to be clever about retaining more labels because the unanimous labels, we're modeling real world entities. So the labels on the representative records tend to be accurate even as we slightly change the definition of representative records. So the labels that we accumulate as we regroup those source records tend to be very consistent. Getting these conflicting labels is kind of a rare case. We're usually able to retain more than 90% of the labels on representative records. And those last 10%, it's better to just get more training data, which we'll do through the active learning process anyway. Which brings us to blocking. So the challenge with adjusting blocking is that as we adjust the block boundaries and as we change the blocking clauses, we can end up eliminating pairs. So subject matter expert review, as with pre-grouping, it may revise the notion of obvious non-matches. We may want to change those block boundaries. In particular, as we scale the data up, we may realize we don't need as much recall. We pull those boundaries in, make the blocking clauses stricter so that we're not generating as many pairs. That eliminates a bunch of pairs, but training labels might be on those pairs. So what do we do? Our approach to addressing the loss of pairs that might contain training labels is to store those pairs separately. We store the data associated with the records on those pairs, as well as the labels in their own data set. It has a complete copy of the data. Those training labels can only be manually updated or deleted. We don't automatically delete those or change those labels. The only thing that we do there is that migration for the pre-grouping model when we change the grouping criteria for the pre-grouping model. Third is, again, for the blocking model, we need to address pruning. We started with a blocking model that was deliberately oriented towards extremely high recall. As we increase the data scale, it becomes more and more important that we still get high recall, but with commensurately high pruning or high efficiency from the blocking model. That is, we want the blocking model to eliminate as many obvious non-matches as possible. Blocking is very sensitive to the thresholds, and the best clauses might not make sense to humans. So our approach here is to actually use the subject matter expert that we've accumulated in terms of clusters and cluster labels to go and derive the blocking model automatically. We observe that clusters can be recreated even with missing edges, missing pairs, which means that we don't need 100% perfect recall. We just need extremely high recall. And we have a process whereby we can automatically derive blocking clauses from subject matter expert clusters or from all clusters or a subset of the clusters, where we can guarantee that that blocking model covers 95% plus of the pairs that will allow the clusters to be recovered, even though it doesn't have perfect recall. This allows us to prune the clauses and prune those extraneous pairs and keep the pruning efficiency as high as possible. Finally, consolidation. Once the model starts to converge, we want to tune the consolidation model. One of the challenges here is that a small change of the consolidation model can impact millions of records. If I change my source priority when I'm assembling data across all the records in a cluster into the final output, that change in source priority may impact millions of records. A subject matter expert needs a way to view what those changes are so they can understand the impact of the changes that they're making. The subject matter expert also needs a way to directly express rules. Some of these rules have subtle constraints in them. So we give our subject matter experts a way to view deltas, to view the changes that are going to be affected by changing rules, and a way to edit values in a user interface. So they have a user interface to view the delta between current and proposed rules, and they have a high-level rule language where they can readily express things like, I need address, city, and state to come from the same record. We're almost ready to train a new model at this point. We need to take our cluster feedback, which comes from SME review and active learning, and turn that into training data. The challenge here is that machine learning can't use cluster labels. We have a lot of really valuable input from our subject matter experts on clusters, but the machine learning requires labels on pairs. So we need to derive pair labels from cluster labels. Naively, I could say that any two records that are verified in the same cluster are a match. For large clusters, that's going to get us a lot of match labels, k-squared match labels, which is too many. For non-match, I could naively say that any record verified in one cluster is a non-match for any record verified in another cluster. Most of those non-matches are going to be trivial, so we need a way to find non-trivial non-matches. For non-matches, we find non-trivial non-matches by looking at where the judgment has changed over time about whether two records belong in the same cluster. That's a solid indication that it's a hard judgment to make and that those two records are on that decision boundary. So we look for cases where two records were in the same cluster, either verified by a human in the same cluster or the machine learning put them in the same cluster, but they are now verified in different clusters. So they're verified as being different, but at some point in the past, either the machine or a human made the judgment that they were the same. Those are our non-match labels. And then for match labels, we do in fact take any two records that are verified in the same cluster. We in fact don't prioritize those by similarity because high similarity records are likely to be identical. They are records that are going to be grouped together by that pre-group by model. And records that are very dissimilar might be missing edges that we never expect pair generation to generate, and we don't expect our classifier to need to make a judgment on. So we're going to select a completely random sample from the match pairs inside a cluster and from the non-match pairs in between clusters. We want that subset of sampled matches and non-matches to be stable. Data is going to change over time. We're going to add records. We're going to delete records. Data in the cluster is going to change over time. We want those changes to minimally perturb which labels are available, which labels are derived from the cluster as training labels. So we use min-hash to select an unbiased stable subset. We select 10 match pairs and 10 unmatched pairs or non-match pairs, which ensures that for small clusters, pretty much all of the match and non-match pairs are selected. And for large clusters, we're taking just a few so it doesn't end up dominating the small clusters. And this produces unbiased training labels. That addresses bias in the training labels, we also need to address bias in the data subset that we have chosen. The selection that we have done to, for example, a limited number of geographies may have filtered out interesting cases. For example, when someone moves from one geography to another, and now I need to find records across that move and cluster them together. It may also have missed interesting cases. If I filter to a geography of people who follow European ancestry and they have a single family name, I miss cases of people that are coming from a Mexican ancestry and they have many family names. So our approach here is subject matter expert guided labels from the new subsets. That is, we take the same search and filter capability that we used during that bootstrap phase, and we use that to find interesting cases coming from the new data that we've just added. And we have the subject matter expert work with us to label a selection of those novel cases. Finally, we're able to do our supervised learning. We have a bunch of labels. The labels cover our new data. They cover interesting cases. They cover active learning. They cover subject matter expert corrections that they have made to the previous output. But machine learning training requires a lot of specialized knowledge. You need to select a model. You need to select hyperparameters. You need to deal with training bias and overfitting and accuracy measurement. And these are all aspects of knowledge that our subject matter experts don't have. Rather than paying to train somebody or bring in an expert who is able to pick all of these things, we observe that we are in a relatively fixed domain. We're doing entity resolution for a single kind of entity. These are people, these are organizations, these are products. So we choose a fixed model. And that fixed model is embedded within the platform. It's a random forest with 5 subtrees. We've chosen all of the hyperparameters. We also automate all of these standard techniques for managing training data. We're doing k-fold learning. We're doing bagging. We're doing pruning. We're managing holdout sets to measure in-sample accuracy. We're taking care of all of that stuff under the covers with a bunch of values and thresholds that are chosen from experience to go and perform this supervised learning. The net is that that subject matter expert can just click a button, the training happens, it takes a few minutes, and then they get a new model, which brings them back to that apply models. They apply the models, they can review the output of this new generation of model on the expanded data and repeat the refine cycle. At some point, the subject matter experts are reviewing the full-scale data. We're no longer processing a subset of the data, and the model has converged, and the subject matter expert believes that the machine learning is producing high-quality results consistently. That brings us to a validation phase of the workflow. The goal of validation is to gather metrics that we can provide to the rest of the organization to help them understand how well they can trust the output of our entity resolution workflow. One of the big challenges here is that we don't have substantial ground truth, and most metrics require substantial ground truth. We don't want to use the training data because that will give us biased metrics. So our approach here is to request subject matter expert labels for validation, specifically for use in validation. We want to keep this small because we value our subject matter experts' time, but we do need to expand the ground truth that we're going to use to compute validation metrics. We're going to select a uniform random sample of records per iteration. And this uniform random sample is relatively small. It's about 10 records per iteration. As you recall, in the refine portion, the refine phase of the machine learning workflow, we're iterating many times, about 20 times. So this will accumulate about 200 records over the course of the refine phase. For each of those records in that sample, the subject matter expert will verify the clusters. This looks just like the activity that they are doing for the active learning to support active learning. The data is going to be used slightly differently. They're verifying that records are correctly clustered, or in the case that they're not correctly clustered, they're moving them to the appropriate clusters. And it's important that the subject matter expert look not just at the cluster that contains the test record, as we call them, the record in the sample for validation, but also all records in similar clusters, so that we can be certain not only that the correct records are in the cluster, but that similar records are correctly not in the cluster. We find that after about 10 rounds or 100 labels, the error bars around the metrics that we compute start to converge, so we start to get meaningful metrics here. And note that validation labels are excluded from training, and training labels are excluded from validation in order to eliminate bias. Now, what metrics are we going to compute? One of the challenges here is that most metrics are biased. Metrics on pairs overcount large clusters. You've got the k-squared inside the cluster. So large clusters generate a lot of pairs, and they tend to dominate estimated metrics. On the other hand, metrics on clusters tend to undercount large clusters. There are many more small clusters than large clusters. Large clusters have a lot of records in them. So a cluster-based metric will tend to undercount large clusters. We want something that is balanced, that is neither going to under nor overcount large clusters. Our approach here is to present a record-oriented metric that is comparing the machine learning versus the human labels. The human labels are the ones that we just gathered for that sample for validation. There are two things that we're interested in. We're interested in precision errors, which is where the human and the machine learning put the record in different clusters. Precision is when they put them in the same cluster, and precision error is when they put them in different clusters. So you can see in the bottom on the left an example here where machine learning has clustered the test record R3 in with R1 and R2, and then the human has placed R3 in a separate cluster from R1 and R2. We're using set overlap to determine the mapping, the alignment between clusters. So this is a Jacquard similarity. And we find that the most similar cluster to the machine learning cluster that contains R3 is the human cluster that contains R1 and 2. This does not contain R3, so this is a precision error. Conversely, recall is when a human and the machine learning put the same records in the cluster with the test record. So a recall error is when a human and machine learning do not put the same records in the same cluster. And in the middle on the bottom, you can see an example of a recall error where machine learning has placed the test record R6 in a separate cluster from records R4 and R5, whereas the human has placed those three records together. Again, set overlap aligns the human cluster with the machine learning cluster with R4 and R5, which says that there is a recall error. The machine learning has failed to recall the similarity between R6 and those other two records. And then on the right, note that you can have a single test record that has both a precision and a recall error. That's the end of the machine learning workflow. Those validation metrics enable us to give highly accurate metrics at scale with a very limited amount of additional ground truth coming from subject matter experts. How do we measure success? There are two interesting metrics of success here. One is how many training labels does it take for the model to converge on a consistently accurate model? And the answer is about 1,000 training labels. And we're able to train a highly accurate model that works on this large-scale data through a combination of handling the easy cases using pre-grouping and blocking. Pre-grouping handles obvious matches, blocking handles obvious non-matches, so we don't need to train the model to handle those obvious cases. This allows the training to focus on the decision boundary, the interesting cases, the hard cases, where we really want the machine learning. The second metric is how long does it take to get a model into production? And typically this can be done in under 2 weeks. There's a fairly subject matter intensive phase at the beginning where we're initially accumulating the training data and doing a lot of navigation of the data set. Once the data engineer who's running this machine learning cycle understands how to expand the data, it becomes a little bit lighter touch with the subject matter experts, just requiring them to provide feedback on the active learning and the validation test records, as well as any corrections for the machine learning, but without the constant oversight over data scoping and expanding the data subsets that are used. But this is fantastic. A model in production in under 2 weeks on a really hard problem like this. So in this part, we have covered effective learning. We talked about what is effective, what is learning. We talked about the three phases of the machine learning workflow: the bootstrap, the refinement cycle, and validation. And as our measures of success, we described being able to produce a model that has excellent accuracy with fewer than 1,000 training labels and to deliver a production model in under 2 weeks. That's the end of part 4 of our 5-part series. Join me again for part 5, where we talk about coping with change.